This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of future MCAT videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover the periodic table trends and then go over the really important groups in the periodic table. First, we need to establish what valence electrons are, and valence electrons are the electrons that are in the highest energy level for an element. And all of that was covered in the electron configuration video, so go watch those if you don't know what energy levels are. But if we look at sulfur underneath the table, for example, so if we look at sulfur's electron configuration, we see that its highest energy level is energy level 3. So then all we do is add up the number of electrons that are in energy level 3 to give us the number of valence electrons. So it has 2 3s electrons and 4 3p electrons, so it has a total of 6 valence electrons. That's how you find it using the electron configuration, but you also want to be able to use the periodic table to find the number of valence electrons. And here we have the periodic table written that has the ending of each element's electron configuration written inside of the box. And if you're unfamiliar with this periodic table, go back and rewatch the electron configuration videos, and this table, that video goes over how to fill out a table just like this. And what this shows us is that each row number corresponds to the highest energy level for the elements that are in that row. So for example, like row 3, the highest energy level is 3. And for row 4, the highest energy level is 4. So then starting on the far left on the periodic table, those elements only have 1 electron in their highest energy level. And then if we go to the right to the next group, those ones only have 2 electrons in their highest energy level. And once you hit the transition metals, notice how the additional electrons are going into the D subshell, and it's 1 energy level lower than the highest energy level. So for row 4, those additional electrons are getting added to the 3rd energy level when the highest energy level is 4. So all of the transition metals only have 2 valence electrons. But once we get to the P block, those electrons are getting added to that highest energy level again. So then we start counting again with 3 electrons, and then 4 valence electrons, and we're just adding 1 valence electron every time that we go to the right. And then once we reach the end, that will be 8 valence electrons. And 8 valence electrons is really important because once an element gets 8 valence electrons, it has an octet. And an octet is very, very stable for an element. So elements do things that is going to help them get an octet. And that really guides the way that elements react. And it's part of the explanation for a lot of the trends that we'll see in the periodic table, which is what we're going to go over right now. So I switched out the other periodic table for a normal one, because a normal one will be better to look at while we talk about these trends. And the first trend that we're going to look at is the effective nuclear charge. And the effective nuclear charge, what it basically tells us is how much of a pull does the positively charged nucleus have on the negatively charged electrons, and specifically the outermost electrons. So basically, how strongly does it pull on the valence electrons? And the way you want to think about this is that all the electrons that are between the valence electrons and the nucleus are shielding the valence electrons from the nucleus's positive charge. So we find the effective nuclear charge by doing protons, which we get from the atomic number, minus non-valence electrons. So protons minus non-valence electrons, and that gives you the effective nuclear charge. And to get the number of non-valence electrons, we first assume that the element is neutral, so the total number of electrons are just going to be equal to the atomic number. So for the non-valence electrons, that's going to be equal to the atomic number minus the valence electrons. And then you want to find your valence electrons just how we discussed earlier in the video, which was 1 for group 1, 2 for group 2, 2 for all of the transition metals, and then 3 through 8 in the P block. So then real quick, let's just do magnesium, for example. Magnesium would have 12 protons minus 10 non-valence electrons because it has 2 valence electrons. So we would do 12 total electrons minus 2 valence to give us the non-valence, giving you an effective nuclear charge of 2. So 12 protons minus 10 non-valence electrons. The next trend we'll look at is atomic radius. In atomic radius, what that is basically telling you is the distance from the nucleus. So there's a positively charged nucleus to the valence electrons. So it doesn't matter how many electrons are between the nucleus and the valence electrons. All that gets considered for the electron cloud is how far away the valence electrons are. And you want to be aware of two trends, and that is what happens when we go up and down on the periodic table, and then the trend that we see as we go left or right on the periodic table. And so first, when we think about the vertical trend, we just want to reference the electron configurations of all these elements, and remember how the rows correspond to the energy levels. So row 1, the valence electrons are in energy level 1. For row 2, they're in 2, and then that just continues. Each row, the valence electrons are in one higher energy level. So by definition, as the energy level goes up, the electrons get further and further away from the nucleus. So the trend is that as we go down the periodic table, the energy level increases, so then the atomic radius also increases. The trend as we go left to right, that is probably best thought about by just referencing the effective nuclear charge, because remember that the effective nuclear charge tells you how strong of a pull the nucleus has on the valence electrons. So the stronger that pull is, then the smaller the atomic radius is going to be. And again, that has to do with the fact that we have more protons as we go to the right, but we are within the same energy level, so then that pull gets stronger and stronger. So as you go to the right, the effective nuclear charge increases, so then the pull gets stronger, so the atomic radius decreases as you go to the right. The last trend is electronegativity, and electronegativity tells you when you have two elements that are in a bond, so I'm just going to use X bonded with Y. Electronegativity tells you how much the element pulls the electrons that are in that bond. So if we pretend that Y is more electronegative than X, the electrons in that bond are going to tend to gather around Y more so than X, because Y pulls those electrons towards it. And for this, we can just think of the atomic radius to explain this one. So as the atomic radius gets smaller, then the atom is going to pull on the electrons stronger. So your trend for increasing strength in electronegativity is the exact opposite of atomic radius. So as the atomic radius gets bigger, electronegativity goes down. So that means that as we go to the right on the periodic table, the radius goes down, so the electronegativity increases as we go to the right. And then as we go down the periodic table, the atomic radius increases, so then that means the electronegativity decreases as you go down the periodic table. The next two trends we'll look at have to do with the elements trying to achieve the octet. So if you need to understand the octet, just go back to that part of the video before you look at these two trends. The first one is the ionization energy, and this is how much energy we need to remove one electron from an element. Elements will do things to try to obtain an octet, and sometimes that can be losing an electron. So if we look at an element like sodium, sodium has an electron configuration that ends in 3s1. So its highest energy level is 3, but it only has one electron in it. And if we write the rest of the configuration for that, that would be 1s2, 2s2, and then 2p6. So if sodium loses one electron, then its highest energy level becomes 2. And then it has a full octet in the energy level 2 because it would have a full S subshell and a full P subshell. So sodium actually really wants to lose an electron because that will help it get a full octet. And if we go to the right to magnesium, magnesium will have the exact same electron configuration, but it's going to end in 3s2. So magnesium would want to lose 2 electrons. And as you continue to go to the right, you just continue to add more electrons. So we'd go from 3s2. The next one is aluminum. Aluminum would have 3s2 and 3p1. So now aluminum has 3 valence electrons. And then every time you go to the right, you're adding one more electron. So you're getting further and further away from just being able to remove an electron to get the full octet. So as you go to the right, the elements get less likely to want to lose an electron. So it takes more and more energy to remove that one electron. So as you go to the right, the ionization energy increases. And then as you go down the periodic table, the energy level increases, like we said before, so the electrons are getting further and further away from the nucleus, which makes them easier to take off of the atom. So it requires less energy to pull an electron off of an element as you go down the periodic table. So the ionization energy decreases going down because the electrons are further away from the nucleus, and that's explained by the electron energy levels. The last thing to point out, we've already kind of talked about, but that's that all the group 2 elements, if they lose 2 electrons like we had for magnesium down here, if it loses those 2 electrons, then it has an octet. Where if sodium were to lose 2 electrons, it would actually ruin an octet, because sodium obtained an octet by losing that one 3s1 electron. So if it loses another electron, it's actually going to ruin the octet. And so we have this term called second ionization energy. So second ionization energy. And what that tells us is how much energy is required to remove a second electron. And group 2 actually has a lower second ionization energy than group 1, because when it loses 2 electrons, it gets to the octet, where group 1 would be ruining an octet to lose that second electron. However, even for magnesium, the first ionization energy is always lower than the second. So that's for every element, including the group 2 elements. The next trend we'll go over is electron affinity, which is kind of like the opposite of ionization energy, because it's how likely is an element to gain an electron. And we're going to use the octet to describe the trend for going to the right on the periodic table for this one. So recall that as you go to the right, the number of valence electrons is going up. So we have 1 for group 1, 2 for 2. All the transition metals have 2 valence electrons, and then it's 3 through 8 again. So as you go to the right, you're getting closer to the octet. So elements that are in, let's say, group 17 have 7 valence electrons. So if they gain 1 electron, they're going to have an octet. And that makes them really, really likely to gain an electron, which means they have a really high electron affinity. So as you go to the right, you get closer to that octet. So then the electron affinity increases, because elements are going to be more likely to try to get to an octet by gaining electrons. And then as you go down the periodic table, we want to think about the electron energy levels again. And it goes up, like we said, as you go down. So then the electrons are getting further away from the nucleus, which makes it harder to gain an electron. So the electron affinity decreases as you go down the periodic table. Now we'll talk about some of the really important groups in the periodic table and some of their behaviors and characteristics. A lot of these are going to fall right in line with the periodic table trends that we just talked about. So try to make the connections between the trends and what these groups do. So starting with group 1, so this first column, we have the alkali metals. And remember from what we just talked about, the alkali metals will try to gain an octet by losing 1 electron. So that means that a lot of times alkali metals are found with a +1 charge, because they've lost that electron and gained an octet by losing the electron. And this makes them very reactive. Since they only have to lose 1 electron, they are extremely reactive, and you really can't even find them in nature without the +1 charge, because they've all lost 1 electron to get that octet. And then group 2 are the alkali earth metals. And like we talked about earlier, these will be really likely to lose 2 electrons. So they're usually found with a +2 charge, and they're very reactive as well, for all the same reasons that the alkali metals were. Now we have our transition metals, which remember is this block here. And remember that transition metals have electrons that are in the d subshell. Electrons that are in the d subshell are lost pretty easily. The atom is not holding on to the d subshell electrons very well. So transition metals are often found with a positive charge. But to go along with this, we need to point out one really specific thing that they do. When a transition metal loses electrons, the first electrons that it's going to lose are from its s subshell, so the highest energy s subshell. If we look at row 4 right here, remember that we have 4s for these 2 elements, and then we start adding for the transition metals into the 3d subshell. But if any of these elements in this 4th row, any of those transition metals lose an electron, it'll lose it from the 4s first. And then once the 4s is empty, which sometimes that could be 4s1, usually it's going to be 4s2. So usually it's going to have to lose 2 electrons from the 4s before it can lose any electrons from the 3d. And transition metals can lose electrons from the d subshell, but not until they have lost all the electrons from their highest energy s subshell. So give some thought to what the electron configuration would be for some of these transition metals if they had like a +1 or +2 or even +3 or 4 charge. The next really special thing about these is that they can absorb UV invisible light, but only if they're in a compound. So if you have one of these transition metals and it's in a compound with another element, then there's a good chance it's going to be able to absorb this UV or visible light. And this has to do with the electrons that are in the d subshell. You don't have to really know about the explanation for this, but just know that the d subshell is what helps to explain this. And it has to do with those electrons absorbing the photons that are in the UV invisible light spectrum. So go back to one of the earlier videos if you want to see how electrons and photons interact. And lastly, the transition metals are really good conductors because the electrons that are in the d subshell are not held very tightly, so they're able to bounce around, which means that if we introduce a current, then the electrons that are in a substance made of a transition metal, those d subshell electrons, will be able to move through that substance, which is what electricity basically is. Next, we have the halogens, which are group 17 all the way over here. And like we talked about with electron affinity, elements on the right side of the periodic table are trying to gain an electron to get the octet, and group 17 only needs to gain one electron to get the octet. So they almost have always accomplished that. So usually the halogens are found with a -1 charge, and they're really reactive because they'll gain one electron really easily to get the octet. And lastly, we have group 18, which are the noble gases. They already have a full octet because they have 8 valence electrons, which makes them extremely unreactive because if they react, they're probably going to lose the full octet, so they really don't react with anything. And this can make them really hard to detect. So that's all we have for the periodic table groups and the trends. I would recommend looking at the trends and the groups and then try to make all the connections and explain all these group behaviors by using the trends that we went over. And then try to explain those trends by using the idea of elements trying to get to the octet, and then also the energy levels from the electron configurations for the elements.